All right, welcome everyone to another edition of Remote High Energy Lunch Seminars. Our speakers today will be Dr. Bailey Tetarenko and Dr. Vittorio Ghirardini. Our first speaker is Dr. Tetarenko. She is currently a McLaughlin Fellow at the University of Michigan in Ann Arbor. She completed her PhD in 2018 at the University of Alberta in Edmonton, Canada. Her research focuses on the study of physical processes governing astrophysical accretion disks and X-ray binaries in our galaxy, with an emphasis on understanding mass inflow and outflow and X-ray irradiation heating using multi-wavelength ground and space-based observatories. She is currently on the job market and actively looking for a new position to start in fall 2021. All right, so please do begin.
Thank you. Let me just share my screen here.
Are you able to share your screen? Okay, good.
All right. Good afternoon, everyone. My name is Bailey Tetarenko, and today I'm going to talk to you about using optical spectroscopy to map the accretion disks in low mass X-ray binary systems. So to start off, we'll go through a little bit of background. So throughout their lifetimes, many astrophysical objects grow and evolve by accumulating mass through a disk. This process, known as accretion, is one of the fundamental building blocks of our universe, responsible for the growth and evolution of objects across astrophysical scales, from newborn stars and planets to supermassive black holes at the center of galaxies. Now, astrophysical accretion disks provide the optimal environment to probe the underlying physics governing this process. However, our understanding of the inner workings of these disks, both the inflow of matter through them and the outflows driven from them, remain fragmented due to gaps in underlying theory and missing observational constraints. Now, compact binaries in which stellar remnants such as black holes, neutron stars, and white dwarfs accrete matter from disks fed by nearby low-mass stars are ideal laboratories to remedy this problem. These binary systems undergo recurrent bright outbursts driven by episodes of mass transfer from the companion star to compact object. This provides us with the unique opportunity to study the evolution of accretion disks in real time when they are observable across the electromagnetic spectrum over short month to year timescales. Now, the mechanism behind these outbursts can be broadly explained with the disk instability model, whereby such transient behavior is explained via the accretion disk cycling between a hot ionized outburst state and a cool neutral quiescent state. Now, this limit cycle, triggered by the accumulation of matter in the disk as a result of mass transfer from our companion star, heats the disk until a significant portion is ionized. Now, the viscosity of the disk, i.e. its ability to move angular momentum outward, increases dramatically when it's in this ionized state, ultimately resulting in a rapid infall of matter onto our compact object and in turn the bright outbursts we observe. So today I'm going to talk about how we can use a combination of multi-wavelength photometry and phase resolve spectroscopy taken during an outburst period as powerful diagnostics to study the highly complex time-dependent accretion disks in compact binary systems. Now, while we now have the ability to image their supermassive relatives, compact binaries are far too small and distant to be imaged directly. However, phase resolve spectroscopy can provide an alternative diagnostic to study their accretion disks. Strong disk-formed optical emission lines are the primary spectral feature of compact binary systems. As a result, it has now become standard practice to use these emission lines observed in compact binary spectra to trace accretion disk dynamics. However, the physical process producing these accretion signatures in many types of compact binaries still remains somewhat of a mystery. It's for this reason that compact binaries harboring stellar mass black holes, i.e. our black hole low mass X-ray binary systems, are of particular interest. Now, most of the optical and infrared light emitted by their accretion disks comes from reprocessed X-rays that are produced close to the black hole and then heat the outer disk regions. This X-ray radiation is the dominant factor determining temperature over most of the disk during outburst. By illuminating the disk surface, this irradiation heating controls both the overall outburst evolution from peak to quiescence, as well as the amount of mass that's actually accreted during the outburst itself. Now, in addition to their spectra, the physical effect irradiation heating has on low mass X-ray binary disks can also be illustrated through their outburst light curves. the temporal profiles actually encode within them distinct observational signatures of their X-ray radiation source heating the disk in the system. Now, the light curve profile for an outbursting disk, as you can see on the slides, can be characterized into stages via the disk instability model, where each stage is defined by how and on what time scale matter moves through the disk itself. Now, a combination of the initial viscous decay stage, as displayed in the pink, and the transition to the following radiation-controlled decay stage, as displayed in the green, offers the ideal means to study both the source of the radiation and its effect on the disk. Now, during the viscous stage, X-ray radiation is at its strongest, and the entire disk is thought to be in a hot ionized state. So here, mass in the disk itself is thought to change only through central accretion of matter onto our compact object. Now, the transition to our second radiation-controlled decay stage occurs as the result of the temperature dropping in our outer disk regions. The resulting cooling front then propagates inward at a speed controlled by the strength of our decaying X-ray irradiation. Now, as physical conditions for the production of emission lines requires the existence of a temperature inversion in the upper disk atmosphere, or chromosphere, this irradiation has long been thought to be the likely physical process behind production of these lines in low mass X-ray binaries. Now, specifically in the case of LMXBs, our accretion signatures take the form of strong hydrogen and helium recombination lines observed at optical wavelengths. You can take, for example, the optical spectra taken during the 2015 outburst of black hole V44 SIG, as you can see on the slides, where it displays a plethora of hydrogen and helium emission lines. Now, typically, these emission lines show double peak profiles as a result of Doppler shifts associated with the roughly Keplerian velocities in our accretion disk. Now, these line profiles are both time and velocity dependent. Take, for example, during the 2018 outburst of black hole MAXI J1820, as you can see on the slides. And look at on the right of the slide, you can see the evolution of our H alpha and one of our helium-1 lines. Now, as a result of their time and velocity dependence, these line profiles can give us information about the distribution of emission over the disk surface. The strength and profile shape of each of these lines encode within them a projection of the disk itself along the line of sight. Now, as the spatial distribution of line emission is a tracer of structure in the disk, these emission lines can, in principle, be used to determine how matter in the disk behaves and evolves over time. Now, currently, there's no clear empirical demonstration of a connection between the disk form emission lines and the X-rays that are actually thought to power them in low mass X-ray binary systems. Now, the radiation process is most significant in the relatively cool outer disk regions of low mass X-ray binaries. So we're talking greater than hundreds of gravitational radii here. So this makes our hydrogen and helium recombination lines an ideal means to probe its source and the effect it has on thermal properties of gas in our disk. So to exploit this, my colleagues and I developed a program combining phase-resolved optical spectroscopy from the Gemini Observatory with X-ray, optical, and UV spectral and photometric monitoring observations with the Neil Gehrels Swift Observatory. Now, overall, our program is essentially designed to track and quantify how variations in irradiation heating during outburst affect the physical properties of the accretion disk itself through the emission line profiles. So over the past year, we were able to trigger a pilot version of this program on a new black hole candidate, MAXI J0637. Now, as you can see on the slides, my colleagues and I were able to monitor this binary with Swift on daily to weekly timescales through its approximately 8-month-long outburst, obtaining time series optical and UV photometry simultaneously with X-ray spectroscopic data. Now, in addition, we were also able to trigger the Gemini portion of our program, allowing us to obtain optical spectroscopic data simultaneously over 3 individual days of our Swift monitoring, covering the end of the viscous decay and transition in our light curve. Now, the strongest feature we found in our optical spectra was our helium-2 4686 line. So what we decided to do was set out to find the expected existence of a correlation between our X-ray radiation heating the disk in J0637 and key properties of the helium-2 disk emission line that we find in our Gemini spectra. So the first step here is to compute the time series evolution of X-ray radiation heating the disk in J0637. So we've actually done this in 2 independent ways. But before I get into that, we're going to go into a little bit more background here. Now, X-ray radiation of low mass X-ray binary accretion disks plays a dominant role in regulating their outburst cycles. However, despite decades of theoretical and observational efforts, key parts of this physical mechanism remain largely unknown. So the problem is basically threefold. Neither the disk radial profile, nor the geometry of the source heating such disks, nor the effect that illuminating spectrum actually has on thermal properties of the disk are particularly well understood. Now, the answers to these open questions are connected to the changing shape of our radiating X-ray spectrum, the fraction of X-ray flux that's actually intercepted and reprocessed in our outer disk, and the temperature to which the disk is actually heated. So more specifically, what is required is an understanding of how these parameters depend on time and disk radius during a low mass X-ray binary outburst cycle. Now, multi-wavelength photometry provides a promising alternative approach to try and answer some of these long-standing questions. So accordingly, the first method we're going to use on J0637 is actually a technique that I recently developed that uses simultaneous X-ray, UV, optical, and/or infrared light curves to track the evolution of X-ray radiation in low mass X-ray binary systems. Now, example can be seen on the slides applying such a method to the 2009 to 2011 outburst of black hole GX239-4. In this case, we make use of a combination of RXT and SMARTS data. Now, essentially, the method works by directly comparing X-ray light curves, which is a measure of our bolometric luminosity, and in turn, a proxy for a mass accretion rate onto a compact object, against UV, optical, and/or infrared photometry, which provides the only means to directly and accurately measure the radiation flux. Now, this methodology essentially yields a complete empirically based, time-dependent, multi-dimensional X-ray irradiation profile. In the case of GX239 here, you can see on the right of the slides, the time series evolution of our reprocessed fraction on the top panel, and the irradiation temperature in the outer disk in the bottom panel, computed in this case using the V-band light curve, ultimately showing how radiation heating of this disk changes through an individual outburst cycle. All right, so on the left, you can see this photometry method applied to J0637. In this case, we make use of the mid-UV filters of UVOT. So if you're familiar with the instrument, that's UVM2 and UVW2. So again, on the top panel, you can see a reprocessed fraction over time. And on the bottom panel, you can see our radiation temperature in the outer disk over time. Now, for comparison, we have also used the more classic method of fitting the SED with an irradiated disk model. So on the right of the slides, you can see some wonderful work done by my student, Evan, who was able to fit all of the broadband SED of XOT plus UVOT data available throughout the 8-month-long outburst with the disk IR model in XSpec. Now, if you take a look back on the left of the slides and you look at the gray points superimposed on the graph here, these are the results of the SED fitting. And now, as you can see, our two methods, so photometry versus SED fitting, agree actually within a factor of 2 to 3, which is actually the expected uncertainty of our multi-wavelength photometry method in the first place. So that's pretty encouraging. All right, so now that we've got our X-ray irradiation sorted, next thing we want to do is analyze our helium-2 4686 emission in our optical spectra. So in the middle, you can see the Doppler tomogram made assuming an orbital period of 4 hours, which is essentially the upper limit indicated by our broadband SED fitting. On the left, you can see our helium-2 line profiles for the 3 epochs of daily average spectra. Now, fitting double Gaussian profiles to our helium-2 4686 lines, as you can see on the right, we're actually able to find statistical evidence for positive correlations existing between the fraction of X-rays intercepted and reprocessed in our outer disk and both the full width half max and equivalent width of our helium-2 4686 line. In addition, similar correlations also exist between our radiation temperature in the outer disk as well as the full width half max and equivalent width of our helium-2 line, although that's not shown here on the slides. Now, while our small data set really limits the statistics we can actually do with such a hint of a correlation, the fact that we observe statistical evidence for a positive correlation existing between our radiation heating and key properties of our helium-2 4686 line for radiation properties computed using 2 completely independent methods, that's our broadband spectral fitting versus our multi-wavelength time series analysis, suggests that disk-formed emission lines in LXBs is, as expected, driven by radiation, and demonstrated changes in physical properties of our radiation heating over outburst should be able to be imprinted on the recombination line profiles themselves that we observe in optical spectra. Now, obviously, what this pilot study lacks is high-quality sequential spectral data sets obtained throughout outburst. On LMXBs, changes in emission line profile shape as well as defining properties during outburst, have been previously associated with changes in flux, as well as changing shape of the irradiating X-ray spectrum. So ultimately, more spectral data taken over a larger range of time, flux, and spectral accretion state during outburst will allow us to track evolution of disk structures and physical properties as a function of time, and in turn put true statistical constraints on the relationship hinted at here between irradiation heating and disk emission line profiles in black hole LMXBs. So accordingly, the next step involves performing this analysis on a time series resolved series of spectra covering multiple binary orbits. Fortunately for us, we have this spectroscopic data obtained with the Liverpool telescope on black hole MAXI J1820. Now, ultimately with J1820, what we have is a binary with known orbital parameters, as well as coverage over multiple months of the 2018 outburst, specifically March through June of 2018, with several disk-formed hydrogen and helium emission lines detected in the spectra. On the right of the slides, you can see just a snapshot of some of the spectral data that we have over approximately a 2-week period, just to show you the key features that we have in our data set. So that'll be our helium-2 4686 line, along with the Bowen blend, as well as H beta and H alpha. Now, what this data set essentially offers us is the perfect opportunity to put some real statistical constraints on the connection between the line emitting regions of a low mass X-ray binary disk and both the physical properties and spectrum of the X-ray radiation heating said disk during outburst. All right, so in summary, the double peak profiles of the hydrogen and helium recombination lines observed in optical spectra of low mass X-ray binaries can be used as powerful diagnostics for mapping the geometry and structure of their accretion disks. In LXBs, detection of these emission lines during outburst is thought to be a result of X-ray radiation heating the disk. However, up to this point, there was no clear empirical demonstration of a connection between our disk form emission lines and the X-rays powering them. So what we did was combined optical spectroscopy with multi-wavelength photometry of a new black hole candidate system in an attempt to track and quantify how variations in the radiation heating over the outburst affect physical properties of the disk through their emission line profiles. Now, triggering our programs with Gemini and Swift on this new black hole candidate, we were able to find positive correlations existing between the X-ray radiation properties heating our disk and key parameters of the detected helium-2 4686 emission line. Now, these results essentially provided both empirical evidence for helium recombination line profiles in low mass X-ray binaries being caused by irradiation of the disk, as expected, and demonstrated that changes in physical properties of the irradiation heating of the disk over a low mass X-ray binary outburst cycle should be able to be imprinted within the helium profiles themselves. Now, while this pilot program presented here is the first crucial step toward our overall goal of developing a method to use phase resolve spectroscopy to effectively probe the geometry and structure of a gas making up an outbursting LMXB accretion disk, we are plagued by our small data set. Ultimately, future data taken over a large range of flux and during different stages of the outburst decay, where the radiating spectrum heating the disk changes significantly in shape, will not only allow us to place firm constraints on the relationship we have found between radiation heating and disk emission line properties in low mass X-ray binaries, but also allow us to use multi-epoch tomography on higher time and wavelength resolution data, delivering a more coherent picture of accretion disk dynamics that the one-off maps produced here do not. Thank you.
All right, thank you for an excellent talk. We have plenty of time for questions. If you would like to ask Bailey a question, either raise your hand in the participants window, or you can send a text in the chat and I'll ask it directly. I guess I'll begin with, for the future work that you mentioned, what do you think the biggest technical challenges are going forward?
Well, I guess it's not going to be the method. So I've established the actual method in being able to create these correlations between X-ray radiation and emission line profiles. But I think ultimately right now, the major issue is if you've ever worked with photospec on the Liverpool telescope, you know that cosmic rays are a serious issue with the data. So right now we're just trying to deal with that at the moment. But once I get the data fully reduced, it should be pretty easy to create these correlations because we have such a wonderful data set and including multiple hydrogen and helium lines. So I'm pretty excited to be able to work with that.
Again, we've got plenty of time for questions, so please don't be shy. Josh? Josh, I think you might be, yeah, you're muted. So let's unmute you.
Here we go.
Okay.
Okay, Bailey, that was a very nice talk. Thank you. I have a question on H-alpha versus helium-2 profiles. It looked as if only the helium-2 was double peaked, but I would have thought H-alpha would be also. Can you comment on why that would be the case? And a second question, which I don't think you did talk about, is these same systems in quiescence, which is, of course, a very different mode with a very strong coronal contribution, and but still some disk contribution. Helium-2 is never seen. So those are somewhat related questions, but if you could respond to either or both, that would be great.
Okay, so are you talking about the MAXI J0637 data specifically?
Yeah, I think that was what it was. It may have been also the case for 1820. I don't remember.
Okay, so I'll start with MAXI J0637. So actually, we only found a strong helium-2 line in the spectra. The H-alpha region was actually quite noisy. So there may have possibly been a little bit of H-alpha contribution there, but it was really unclear. So unfortunately, we weren't able to do much with the possible H-alpha emission in the J0637 spectra.
Okay.
As for MAXI J1820, actually so just in the spectra that I showed on the slides, that's only actually over a couple of weeks. But looking at our entire spectral data set, the H-alpha actually changes in shape quite a bit between more double peaked down to a single peak. And I think this is typically what we're going to expect because we have so much data covering a wide range of accretion state from soft through hard. So we should be able to see a really nice evolution of both the H-alpha as well as the helium-2 emission line shapes throughout our spectral data set of 1820. So that should be pretty exciting to get to work with.
Wouldn't H-alpha be more likely to be double peaked than helium-2?
Why would you say that?
Well, it's predominantly coming from, actually, this is an argument that it wouldn't be, but it's presumably coming from outer regions of the disk, whereas the helium-2 would be innermost, but I would expect the helium-2 might be not resolved as double peak, just a very broad feature, which is what I thought one usually saw.
Well, well, we do see it double peaked in the 1820 data. So
Okay.
Okay, we should move on to our next speaker. So, thank you again, Dr. Tetarenko. And our next speaker is Dr. Vittorio Ghirardini. And he he earned his PhD at Bologna in Italy with Stefano Ettori. He was a postdoc at the CFA with Ezra Bulbul, and is now a postdoc at the Max Planck Institute for Extraterrestrial Astrophysics, extraterrestrial physics with Ezra Bulbul. And he'll be speaking about the first year of eROSITA observations, the first results on galaxy clusters and groups.
Okay, so I would like to first thank the organizers. Wait, let me share my screen. I would like to first to thank the organizer for this opportunity of giving this talk. And I will going to present some of the few first results that eROSITA has already found on galaxy clusters and galaxy groups. So as you might know, eROSITA is an X-ray instrument, is an X-ray telescope on board of SRG, Spectrum Rontgen Gamma, which is a German-Russian spacecraft which is orbiting at L2. In this talk, I will not focus just on eROSITA, which is the main instrument on SRG. There is another instrument just for you to know on SRG, which is RTXC, which is a Russian instrument, which is there to study hard X-ray. So it will do a hard X-ray full sky survey. So eROSITA is composed of 7 mirrors. So 7 different telescopes that have 7 mirrors, and each one of these mirrors are connected directly to a CCD, which is PN-like, similar to the one on XMM. The spectral resolution of these CCDs is about 80 electron volt at about 1.5 keV. The focal length of eROSITA is relatively short, is about 1.6 meters. However, the field of view of eROSITA is one of its main advantage point, which is the field of view of 1 degree diameter, which is quite big. And also the fact that the PSF, or the half energy width, is about 18 arcsecond on axis, but is about 26 arcsecond average over the field of view. So it's pretty constant overall the 1 degree diameter field of view of eROSITA. Moreover, on each telescope, there are baffles mounted, which allow to reduce the straight light up to 90%, which is particularly important where you're observing close to bright sources in general. So also going on with the properties of eROSITA, eROSITA has a quite large effective area of about 1,300 centimeters squared at 1 keV. And you can see here the effective area as function of energy compared with different instruments. And so you can see here in particular that in the soft energy band between 0.5 and 2 keV, let's say, it's fully consistent. It's basically at the same effective area as XMM, while it loses a little bit at high energy, basically because the focal length is a bit short. However, since eROSITA is already doing the survey of the whole sky in X-ray, it's important to consider also the grasp, which is the product of the effective area average over the field of view times the field of view itself. And when you consider the grasp, you see that eROSITA is much better than all the other telescopes at about 1 keV in order to perform big area surveys. Yeah. So I'm not going to focus on all the goals of eROSITA. I'm just going to display a little bit what are the main goals regarding cluster astrophysics and cosmology. So first of all, we want to do cosmology with eROSITA. So we want to map the dark energy distribution in the universe. And we also want to find whether we can find new physics using by fitting the cosmology using clusters. Moreover, we want to find and investigate the nature of dark matter, but we also want to study some astrophysical processes that involve clusters. So we want to study, in particular, also how, for instance, the WIM accretes onto the outskirts of galaxy clusters, which you can kind of do when you stack close by clusters. And you also want to know how these baryons that fall into the clusters do evolve with cosmic time. And so also that's also is one of the main goals of eROSITA regarding clusters. So eROSITA started, it was launched in July of last year, and started this performance verification phase last year in September, and started the whole-scale survey in December last year. And so there are several observations. There are 3 months of PV observation for eROSITA. However, I will be focusing on just one PV phase observation of eROSITA, which is observing the eROSITA final equatorial depth survey, which is the also called IFEDS field, which is an area which is about 140 square degrees and has been fully covered by eROSITA during just 4 days. And as you can guess from the name, the depth of this survey, it's about the same depth of the final survey of eROSITA after 4 years, or after 8 entire complete scans of the sky in an equatorial field, which is about 2.30 kiloseconds. So it's 2 for the ERAS-8, so the 8 scans of eROSITA. In this case, it's a bit deeper. It's about 2.3 kiloseconds, the average exposure. You can see here the soft energy band of the field in eROSITA. And for scale, you see on the top left, on the bottom left, you see how big is a square degree. And on this field, we run our source detection algorithm. And you see here in green all the extended sources that we are found. But in details, what IFEDS is just a proof of concept of the final depth of the survey of eROSITA, so after the 8th scan. And in this field, we have found a lot of clusters, a lot of extended sources, about 540 sources. And when we estimate the masses for these sources, we see that we can go down to 10 to the 13 solar masses as expected. And in redshift, we can go up to a redshift of 1.2, 1.3. This field was also chosen because there is a very good overlap with optical instruments like HSC, gamma, and decals, and in particular with HSC, which is the main instrument, the IPSC camera on board of the Subaru telescope on Hawaii. We have about 90% full coverage with HSC of this field, so it's a pretty good coverage. And in particular, the important use of having HSC is the fact that we will have very good weak lensing masses for basically most of these clusters. And so we will be able to calibrate quite well the scaling relations. Moreover, we also have recently completed some 12 SDSS plates, which are very useful because this will allow to measure spectroscopic redshift for all of the system, because up to now what we have, I mean, these surveys, HSC, gamma, and decals are mainly giving us, not gamma, but HSC and decals, which are the ones that cover the most area, gives us just some photometric redshift, but still are quite useful. Moreover, this entire field was observed by LOFAR, and in some dedicated pointing, there was also some USGMRT observation, but I will come back to this observation in a few slides. And also in the same pointing of this USGMRT observation, there will be some dedicated NICA2 and XMM observation that will be done in the near future. In fact, NICA2 are scheduled for next week. And these are some preliminary plots of some of the few results on these clusters in this field. So you see in the plot on the left, you see the luminosity distribution with redshift. And it's quite similar to what's actually expected from eROSITA. And you see that we span like 3 orders of magnitude in the luminosity, and we span out to redshift of 1.2, 1.3. The highest redshift is about 1.3, but it's photometric, so there is some uncertainty on it, but not so big. And on the right, you see the redshift distributions of this cluster that were detected. And you see that they peak at between 0.3 and 0.4 in redshift. So the median value is about 0.3, 0.4, but they can go up to redshift of 1.2. So we detected clusters also at very high redshift. And in particular, some of these, so these figures are just part of a few works that will be presented basically early next year by a paper from Eng Liu and Matthias Klein. So for two papers, one from Eng Liu regarding the X-ray part and Matthias Klein regarding the optical part. What I will instead be showing next year will be the morphological properties that we measure from these clusters, which you can see here in the plot in the figure. And we want to investigate the morphological properties in these clusters because morphological properties are a very good indication of whether a cluster is relaxed or disturbed, or in general a cool core or not cool core. That can be a matter of definition, but they are not one-to-one between relaxed, disturbed, and cool core, not cool core. And in particular, it's very important when you want to distinguish between disturbed and relaxed, for instance, that you have some morphological parameters that are more sensitive to the core and some parameters that are more sensitive to the larger scale emission. And in fact, we have few, like central density, which is the value of the density that give a fixed radius, the concentration, which is the surface brightness in the ratio of the surface brightness in two different apertures, and the cuspiness, which is the slope of the density at fixed radius. These are very much sensitive to the properties in the cores, while others like ellipticity, power ratio, and Gini coefficient and photosymmetry are more sensitive to the large scale emissions. From some preliminary results on that, in particular regarding central density, concentration, and cuspiness, which are the one for which we do correct for the PS of eROSITA, is that we find that the distribution of these parameters are quite consistent with the SZ result from, the early result from Lovisari 2017 that analyzed the early SZ Planck sample. And this is quite surprising because the selection of this sample, which is X-ray selected, and the Lovisari sample, which is an SZ selection, is quite different. And in the literature, there has been shown that generally you don't have a matching between the distribution of several properties when you have an SZ on X-ray selection. Moreover, as you can see from basically the diagonal plot in this, the diagonal part in this plot, you see that the distribution of the parameters do not indicate for the moment any presence of kind of bimodality between relaxed and disturbed. And so this kind of indicates that the transition between cool core and not cool core, so between relaxed and non-relaxed, seems to be for now smooth, so continuous transformation between relaxed and non-relaxed. However, keep in mind that this is still work in progress, and so it might change in the future. So another work that was recently submitted was the discovery of the first cluster by eROSITA. And you see on the left image here, the eROSITA image which is basically the easternmost part of the IFEDS field. And you see 8 clusters that are circled in with white circles. And that are basically the same redshift. Basically, all the redshift of this system is about 0.37. And you see on the right, the HSC, so the image from the Subaru telescope camera, but not the image, but the galaxy density map coming from data from HSC. And you see on the same circles are on the left and the right, so the position of the clusters is the same. And you see the striking overlap between the X-ray emission and the overdensity in galaxy at this redshift. So this actually confirms our indication that this is a kind of a supercluster. And you see here the names of the clusters and the redshift. These two are present in the field, but are not at the same redshift. This is at a slight different redshift, and this is why it shows a small signal in the galaxy density map. And some properties of these clusters you can see here in this table. So you can see the redshift, the luminosity that we measure from eROSITA, the temperature that we measure for eROSITA, what are the masses that we can estimate from eROSITA using luminosity mass scaling relation. And you see in the last column, you see how many counts we get for each cluster. These are just the background subtracted counts. And basically, I want also to point out that this is not the only supercluster that we detect in the IFEDS field. In fact, we detect about 3 to 4 more clusters, superclusters in this field. However, this is the one at the highest redshift. and it's also one of its member. The third one here is one of the brightest clusters. Sorry, is one of the brightest clusters in the IFEDS field. And also in this work, we also did some simulation and some forecast for ERAS-8, so the final final eROSITA survey. And we predict to detect about 450 superclusters in the final survey. So I was telling you before that we have some UGMRT follow-up observation on some part of IFEDS field. And if you look at the first system in the north of these superclusters, you see 3 clusters that are very close to another. And in particular, this is basically the distance between the one in the south here and the one here. It's about 7 arc minutes only. So they are very close. And this one here, it's 2 arc minutes from the other one. And we are able to detect all of this using our source detection. And so this detection, the redshift measurement that tells us that are the same redshift, and also the optical image, which you see below the radio contour here, tells us that this system is quite interesting. And in fact, we were able to follow up this system using radio observation. Thanks that to Dewey Hong for doing the radio observation and radio analysis. And other than a radio halo, we also detected 2 radio relics, one located in the north of this system. You see here a zoom in of this region where you see the optical image and the radio contours. And in the south, you also have another radio relic. And from radio data, we were able to estimate what was the Mach number for the shock in these relics that caused the acceleration of particles, basically. And we get the Mach number is quite strong. It's about 2 for the north relic and 3.5 for the one in the south. So quite strong merger. And so since you know that when you have the presence of radio relics, typically you're also associated with a surface brightness jump, we try to actually detect in the eROSITA image whether we see this surface brightness jump. So you see here the eROSITA image smoothed, and you see in red the radio contours, and we extract the surface brightness along the blue direction, which is toward the north relic, along the orange direction, which is the southeast relic, and one just for control, which is in the perpendicular direction to the expected merger axis. However, the signal to noise of eROSITA at this relic position during this survey was quite small, and so we were not able to actually detect the shock in the ACM using the eROSITA data. Moreover, when you have a supercluster, you generally have several clusters which are very close one to another, and so you might expect some emission from the WIM that connects clusters in the node of the cosmic web. And this signal should be amplified when this WIM gets nearby to outskirts of galaxy clusters. And so we try to see whether in the regions, in these green boxes that connect the clusters, whether we were able to detect the WIM. You kind of see some enhanced emission here, but still the signal to noise is not very large. And we are only able to set some upper limit in the actual density, the signal, the gas mass that were present in these regions connecting clusters. I mean, to estimate the gas mass, we had to assume some cylindrical shape of the WIM between clusters, but still, we didn't get any just upper limits on the measurements of the possible presence of the WIM here. So, as you might have heard from the news, the first full sky survey was completed in June this year, and next week it will be completed the second sky survey. And this is just an image of the eROSITA all sky survey, the first eROSITA all sky survey, where you can see some known system, in particular SCOX1 and Virgo cluster, I would point out, other than all the other ones, which are very famous objects, I would say. And on this, I want just to showcase some nice images that were able to be taken, for instance, on the, first of all, I skipped a slide in my head. So first of all, I want to just to show the exposure map of eROSITA, where you see that of ERAS-1. So you see that in equatorial fields, the exposure, so which means that about in this plane here, the exposure it's about 200 seconds, But in the ecliptic pole, due to the survey strategy, so we want to loop around and pass basically 4 times a day around at the ecliptic poles. We have the exposure at the poles is quite deep. In fact, at the pole itself, at the ecliptic pole itself, we have about 36 kiloseconds, which is quite deep survey, while in equatorial field, we have about 200 seconds. So this is just to showcase some nice image of the shapely superclusters from eROSITA during ERAS-1. Credit that to Ezra Bulbul and to Jeremy Sander for making this nice image, where you can see this very large emission for the shapely supercluster. You can see the scale here in the bottom left. So this is quite a big system. And you see here in the panels to the left, some zoomed in parts on some of the most known and studied parts of the shapely supercluster. And so I just want to conclude like that by saying that eROSITA allows us to enhance our view on the entire sky by getting wider and deeper than previously done. And IFETS was a very nice showcase of the capability of eROSITA. In fact, we detected about 3 to 4 clusters per square degree. And also it was showcasing the fact that we can go down to 10 to the 13 solar masses, and we can go up to redshift of 1.2. And also we have discovered a few superclusters, and in particular on the one at higher redshift, we have UGMRT dedicated observations next week, and in this winter in general, we'll have dedicated NICA2 observation in order to measure possible KSZ induced by the merger. And in the next cycle of AAO, so it was accepted with priority C and a proposal that we put forward to observe this supercluster and follow up that with XMM Newton. And so keep tuned, and that's it for me. So I'll take your questions now.
All right, thank you for a very interesting talk. If anyone has questions for Dr. Ghirardini, I see we have at least one hand raised. Mila?
Yes, hi. Vittorio, that was an awesome talk. Thank you. So I had a couple questions. I guess I'll start with, that seems like a lot of superclusters you detected. And I was wondering if there was, if you had sort of a rough estimation of how many you would have expected sort of from like lambda CDM cosmology, and if this is a surprisingly large number, or if this is just about what you would expect. Because if it's more than you would expect, then I'm curious about whether we have to start making corrections for, you know, essentially account for more maybe lensing by large scale structure or things like that as we look at more distant objects. Yeah, basically, is the number of superclusters surprising?
Okay, so first of all, the definition of supercluster, there are several definitions of superclusters in the literature, and they do not tend to not to agree with themselves. What we have taken as definition of supercluster here is taken from Chon 2012 paper, which basically finds clusters based on a linking length, and a linking length is basically related to some cluster number over density. So similarly to us, as clusters are over density of galaxies, we're just looking at over density of clusters, and at fixed above a fixed threshold, you will define what is a supercluster or not. And so this was the definition that we used. I used that definition. That is the number that we found is about 3 to 4 in IFETS. And when we forecasted that to ERAS-8, so to 8 entire sky surveys, so basically the same depth, but on overall the sky, we forecasted about using simulations, using dedicated lambda CDM simulations that were done just for eROSITA testing purposes and forecast for cosmology and calibration of selection function. I mean, they have several purposes, these simulations. But using these numbers that I was telling you were basically consistent with what these simulations were predicting. And so there is no there is no deviation for now. I mean, in the number of superclusters from lambda CDM that we can think of.
That's okay. That's nice to know. And just the second question that I had was the lack of bimodality in the cluster core properties, or I guess in all the parameters that you looked at. So you said that this result is tentative, and I was curious what else, what could potentially change that result?
So basically can be dependent by also, technically by some binning size, for instance, can a bit change because the number of bins, I cannot go back to the slide. Wait a second, I think I can, because the slides are heavy. A second, it should be the next slide. So basically here there are a lot of points. However, there are, I mean, this is just taking all the effects cluster without doing any selection. So basically it's the flux selection of eROSITA. However, when you want to study the morphological parameter distribution, you may want to limit yourself to a redshift bin or to a mass bin. So you don't want to mix them up together, because otherwise you can kind of mix in some evolution with redshift that can smear out your peak, and can also make you misunderstood continuous distribution for what is like actually this continuous distribution, but is overimposed when you have multiple redshift slices and the peaks changes. For instance, if the central density evolves with redshift, let's say it evolves smoothly with redshift between one value and another value, but it's different between cool core and not cool core, and the evolution puts them closer together, then you might actually do misidentify a smooth parameter, I mean a smooth distribution parameter like the one that you see here, with a bimodality which is actually superimposed and cancelled by this thing that you do not consider. So there are a few systematics that needs to be considered in order to actually know whether this is actually a true non-bimodality or just unlucky, let's say, no, lack of bimodality. I hope I was clear and not too confusing.
No, you were very clear. Thank you.
All right, we have a question from Stefano. Please unmute.
Hi everyone, and hi Vittorio in particular. Good to see you and thanks for the talk. Two questions. One is related to the background. Is still stable after 2 years? And what about the features around the iron K that was at some point appeared at some point in the first spectra that were published? If you have any news about what is producing these features. And then a more physical question, more scientific question is related to the effects. I was wondering if you try, it seems there are a lot of structure in effects. So I was wondering if you try to apply different technique to resolve structure at low sulfur brightness. Because so, not all the green point identify over densities.
Okay, so remember me if I forget some point of this question, because I have short memory. So regarding this feature around the iron K line, I have to say that I don't have that present, but I know that in the instrumental background of eROSITA, there is a one line that is present at around 6.4 keV that is caused by some screws that are present on board of the spacecraft, which are made of iron. And I don't know if it's that what you're talking about, but maybe that it's
so so you identify, because at some point there was discussion what was the origin for that, and you are now sure that the origin is due to the screw on the telescope.
Yes, the origin is due to some screw in the telescopes. However, I think there is a small, a slight mismatch between the amount of metal that should be actually required to make that line with the actual weight of the screws. But on that, I'm not completely adjourned. I think I heard this thing a couple of months back last times, but can be changed, I don't know. And regarding the stability of the background, I have to say that I don't know much about that, because I mainly focused on effects that was taken just during 4 days last year. And then on ERAS-1, I was just picking some data from time to time and analyzing some here and some there, but not in too many details, in particular regarding the background. But up to the news I know, the background seems to be stable, yes. A bit enhanced, that was with respect to what was predicted, but still not so enhanced than what was predicted. So regarding the detection of sources in the FEDS field instead, so our detection method is based on a sliding cell. And however, I am aware that there are present different other way to detect clusters or detect extended sources in general in X-ray, in particular wavelet. And there was several challenges at Max Planck at MPE regarding the choice of which code will be used to do the detection of sources and will also be used to do the characterization of the selection function. And up to now, during these tests, it appears to be that this method that has been used is outperforming wavelet detections. And so this is why we have chosen this source detection in order to detect the extended sources in this field, but also in ERAS-1, probably we will also adopt the same code.
Thank you. Ciao.
Ciao.
All right, that concludes our time for the talks. Thank you all for attending, and especially thank you to our speakers. If you'd like to ask them further questions or meet with them for an extended conversation, please email Bailey directly, or if you need to contact her via me, that's fine too. Vittorio has a sign-up sheet on his on the linked from the emails and the website. So he has some time, I believe, tomorrow and the day after.
Yep.
And we have a separate Zoom meeting set up for that. So thank you all, and look forward to seeing the next round of talks next semester.